In this video, we're going to introduce the concept of a reference angle, okay, or a related angle. And in trig, when we evaluate trig functions, it's often better to just use a reference angle than it is to use the actual angle that you're given. We'll talk about that in the next video. But in this video, what is a reference angle? I'm just going to go ahead and throw the definition at you right here. And it is an angle. We say let theta be an angle in standard position. Okay, so like, if I were to sketch this right here, this is some hypothetical angle in standard position. I'll have it, just for emphasis, I'll have my angle terminate in the second quadrant. So here's my angle. I'm going to call this angle theta. Okay, and it's in standard position, so left the positive x-axis, terminate in the second quadrant here. We say that its reference angle is the acute angle, so this is really important here, acute angle, and you notice that I write theta prime. It's a theta with a little apostrophe right there. We say its reference angle is the acute angle theta prime formed by the terminal side of our original angle theta and the horizontal x-axis. Okay, so let's see if I can point this out to you here. On our image over here, where would this be? Well, we said it's the acute angle formed between the terminal side of theta and the horizontal x-axis. Well, we can already see that the horizontal x-axis is right here, and we can see that the terminal side of this angle, of course, is this angle right here. When I say it's the angle formed between the x-axis and our given angle, that could be this angle right here, or it could be this angle right here, but what I can tell you is it must be this angle here on the left, and the reason why is just because by definition we say it has to be the acute angle theta. Okay, so in other words, we say, well, how do you always find the reference angle between a given angle, and the x-axis there? We say it's just always the quickest distance or the quickest rotation back to the x-axis, and we would label this. We would say that this is the angle theta prime. And theta prime related to theta in that it is the reference angle of the angle theta here. And so I want you to imagine, I mean, if this was more dynamic, we could twist this angle around and around and around and around. I mean, if I had twisted my angle down to here, we say where would the reference angle for this angle theta here be? And it would have to be between the terminal side and the x-axis, and it'd always be this acute angle right here. We could say that this would have been theta prime. Okay, so before I kind of proceed here with the definition of reference angles and how to determine them algebraically with this really tedious way to remember, you can actually just sketch an image of it and figure it out on your own. But what I've done is I've got this interactive here. I got it at mathopenref.com, open reference, and you can see that what we're doing is I'm twisting my angle here, and what you see here is that the black angle represents the angle theta. This blue angle on the inside is representing the reference angle between the terminal side of the original angle and the x-axis. But you can see that once I rotate past 90 here, you see how the original angle keeps growing, but the reference angle is always this acute angle that gets formed between the terminal side and the x-axis, okay? And if I were to pop this over 180 degrees, boom. Now my reference angle is down here, okay, between the terminal side and the x-axis there. And if I keep going over here, we see how the reference angle just keeps following this. But you can see how the reference angle, the biggest it ever gets is 90. Like, you could never get more than 90 because by definition it's the acute angle formed between the terminal side and the x-axis. I could keep even more rotation onto here, or we could keep rotating through, and this angle, this terminal side and the x-axis always form this reference angle associated with the original angle, okay? And so oftentimes we are only interested in the reference angle. And really the reason why is because you can see if we were to drop an altitude right here, from here down to here, it would form a right triangle. It's this 42 in the right triangle that we could do SOHCAHTOA on that we care most about. All right, so I'm going to head back over to here. We're going to talk about, well, then how do I find reference angles in the first place, okay? Given, let's say this, I've got some images here, and I'm going to run through some examples down here regardless, but let's look at this one here. It says, the following diagrams illustrate reference angles for the given angles theta. So, for instance, if I wanted to find a reference angle for an angle that terminated, first of all, in the second quadrant, sorry for my horrible picture here. Let me try this again here. Let's say we had a 140-degree angle, which we all, tuning into this, probably realize that is 40 degrees shy of 180 degrees. Notice how I said that there. That'll help you out. We'd say 140 degrees. What I want to go do is, first of all, sketch in the reference angle, which is this guy right here, and then go solve for it. The idea here is this. According to this definition over here, it says if your angle terminates in the second quadrant, this is always how you'll find the reference angle, theta prime. You'll take 180 and you'll subtract off the angle that you were given, either in degrees or radians. If you were in radians, you say pi minus theta. Nobody memorizes this, like nobody does, because we all have common sense. We have reasonability here, and we look at this and we say, look, if this is 140, what is this little leftover portion right here? We know that since this is 180 degrees, we say, well, then let's just take the 180 degrees, subtract subtract off this original orange angle right here, 140 degrees, which is exactly what this definition says right here, and it leaves you behind with 40 degrees. So I know that, and you know, this is wrong for me to say, I probably shouldn't say this, but it's common sense. It really is the common sense being able to find out what your angle theta prime is. All you gotta do is sketch your original angle and put some thought process into it. But if you need definitions, then know that these, in this case, we say quadrant 2, quadrant 3, and quadrant 4. In each instance, here's how you would find the reference angle. You would do these calculations down here, and I'll let you copy those down, okay? But what I can tell you is one really important one to know is they didn't list quadrant 1. The only reason why is because if you're an angle in quadrant 1, let's say this is a 45-degree angle right here, I say that's theta, then what would theta prime be? As a matter of fact, theta prime and theta would have to be equal if you're in the first quadrant, if you terminate in the first quadrant, okay? So, given that, by the way, given that angle theta in the first place is somewhere between 0 and 360 degrees, or 0 and 2 pi, okay? If you go over, you're going to have to do some more thinking there. But what I want to do is I want to sketch these angles in standard position to find the reference angles. So let's do it. We say a 213-degree angle. How could I find the reference angle on a 213-degree angle? I will tell you this. When you sketch angles, it is most important to realize that, and we're in degrees here, that the quadrantal angles are the ones that help you kind of navigate. So if I were to say that's 90, that's 180, this is 270, and this is 0 or 360, however you want to interpret it, what I could tell you is this: 213 has to be somewhere between 180 and 270. And as a matter of fact, I think it's a little bit closer to 180 than it is to 270. So what I'm doing is all I'm trying to do is represent this, you guys. And I say that theta in this case is 213 degrees. Let me try this again here. Equals 213 degrees. Now, according to my definition up here, if I wanted to find this reference angle and it terminates in the third quadrant, what we do is we would take our original 213 here, our theta, and subtract off 180. But again, you know, representing this and using what I shouldn't have said, common sense, this little rotation right here, this theta prime, we obviously could have figured this out by taking our original 213 degrees, 213, and subtracting off the 180 that would have gotten us over to here, and that leaves you behind this little portion right here. This is angle subtraction, angle addition postulates. Okay, so we say, really, this would be a 33-degree reference angle. So we say theta prime is 33 degrees, and we could write that right underneath this. Given a 213-degree angle, its related angle or reference angle is 33 degrees. Okay, so now let's look at these other two, and these are both in radians. And I'll tell you what, radians with decimals, yeah, not so much fun to do. But I will tell you this, if it's in radians with exact values, oh, it's super easy, and we can talk about why. So mind my sketches here. Sorry I had to put them a little bit off to the right. I took up a lot of space there. I'll try to draw this a little bit smaller, but I say, where would 1.7 radians be? Well, what I know is this. This is pi, or 3.14. And, half of that is 1.57, reasonably, 1.57. Okay, so 1.7 radians would be this measurement right here. Okay, so a few things I want to say about this. First of all, our original angle is 1.7. And second of all, the reference angle is not this angle right here. I get a lot of people make that mistake. What we want is the acute angle formed between this terminal side and the x-axis. So here, at least let's get our sketch of our reference angle in here. Here's the reference angle. And reasonably, if I wanted to find this, what we could do is we could take this original 3.14 and subtract off the original 1.7. Okay, so there's no problem in pulling out a calculator here. As a matter of fact, what I'm going to do is this. I'm going to take exactly, literally, pi, which is 3.14, 15926, and we're going to subtract off 1.7. Now, I'm keen on, approximating this here, but we would say that this reference angle would be about 1.44 rad, okay, approximately. I'll put a little squiggly here, 1.44, and just for emphasis here, I'm going to write radians, okay, radians. Groovy. Okay, so this last one where I said it's really, really kind of fun to do reference angles with exact values of radian measurement. We say, all right, so 4 pi thirds. Where would 4 pi thirds be? And then this is actually, I say that these are a lot easier because if this is pi and this is 2 pi, this is really, imagine 3 pi thirds, of course, 3 pi thirds. And this is 6 pi thirds. But to navigate here, we'd say it's at least 3 pi thirds plus another pi third, which in our heads, is a 60-degree angle. But we say, here's our 4 pi thirds radian measurement, and that is our theta. Okay, so our reference angle would be this angle right here. First of all, sketching it in, we'd say that this is theta prime. But the reason why this is so easy, because when you're dealing with, fractions of pi, we say 4 pi thirds, that was a pi third past 3 pi thirds, then this is literally just flat out pi thirds, okay? If we had 5 pi thirds, it would have been over here, and the reference angle still would have been pi thirds. What if we had, pi? What's the reference angle on pi? Well, 0, because you're already on the x-axis. But yeah, we say finding reference angles, not a bad thing to do. As a matter of fact, it's a necessity. We want to be able to find this, because in our next video, we're going to use reference angles to evaluate trig functions. Cheers.